Hi, this is another video in the tutorial of the course Digital Economy and Data Analytics. My name is Eiko Vuren and today we're going to talk about trees-based methods. And in order to start with respect to that, we remember that from the previous tutorial, the videos of the previous tutorial, we have been looking at a website called vanda.nl. And more in particular, we have been looking there at all the houses that are for sale on this particular website on the 10th of October 2025 in Amsterdam. Well, in order to start with respect to that particular website, or maybe better to say that particular data set, what we need to do is, first of all, a couple of different things. First of all, we have to then import pandas. We're going to do that by using import pandas as PD, and then in addition to that we need to write down our directory. That's going to be a string, and that's this string that we have over here. However, that's of course a string that I have in my computer. This most likely is going to be a little different in your case. And then finally what we're going to have is that we then are able to read in the Excel sheet, and that we can do by pd.readExcel. Then we're going to have here our f string, which is, then including, or maybe better to say, pasting in the directory that we have over here. And in addition to that, we are going to have our file name, and that is this file name that we have over here. Well, based on this, we are able to then load in the data, and we're going to load that into a so-called data frame, and the data frame that we are going to call here df over here. So we are going to work with this data set another time in order to look at the trees-based methods that we're going to look at today. And then the first thing we can do is that we can look at trees. Well, one thing we should realize that at the moment that we're going to look at the trees-based methods, then it's not really necessary to make dummy variables for the categorical variables that we have. At least not for the, say, categorical variables that we have that are going to be ordinal, because of the fact that, trees, they can decide themselves how they are going to categorize the ordinal values. So in that sense, we are not going to use dummies anymore here for these, say, ordinal values, like, for example, the year of construction, as well as the postcodes. And in addition to that, we are going to also not have these interaction terms, because of the fact that if we don't have the dummies, then we can also not interact them, for example, with the size of the apartments. So therefore, what we're going to do then is that we are going to start with simple trees, no backing, boosting, or random forests yet. And that implies that what we need to do is that we have to, import from our library sklearn. In this case, it's going to be sklearn.tree. So we're going to have from sklearn.tree, we're going to import decision tree regressor. This is the easiest way to do it, because of the fact that then at that moment in time we can immediately use the decision tree regressor, the method, or maybe better to say the function decision tree regressor. And that we're going to do in the next line, take into account that we at least have to specify one particular thing, and that is the maximum depth that we have with respect to the tree. We're going to set that here, I would say just completely randomly equal to 10. We are going to talk about that much more on the next slides. But that is going to be the maximum depth that we have with respect to the tree, the number of layers that we allow the tree to have. Well, we are going to put this model that we have over here. This is just to define the model that we're going to use, the algorithm that we're going to use. We are going to, store that into this variable CLF that we have over here. We then are going to use, or we're going to do much more with respect to this algorithm CLF over here, because of the fact that the next thing we're going to do is that we're going to do the fitting process. And as usual, that is going to be equal to CLF.fit. And of course, as we had with respect to standard linear regression, as well as with lasso enrich, we're going to have, first of all, the x values. So we're going to have x train, the x values for the training data set, and we're going to have y train, the y values for the training data set. Well, then what we can do next is that we can then make predictions based on the fitted values that we have over here, and we can do that by CLF predict, and we then are going to do that with respect to the test sample. So we're going to do that with respect to the X values of our test sample. I do here X test. I could have keep it like that, but then usually we get very annoying errors, and the reason behind that is because of the fact that this is a numpy array which is say names with it, and well, then you get a very annoying error that says like, well, the numpy array has names, but we are not going to take that into account into say the fitting process, or at least the predicting process that we have over here. Then therefore what I've done here is that I have used here dot values just to use the values of the particular numpy array without the names. This is something that is related to Python, unfortunately, that Python very easily makes warnings, and that can be very well annoying with respect to your output if you have a lot of say warnings every time. And therefore there are two ways to omit that. We can do that by importing a particular library that is called warnings that gives you all kinds of ways in order to say not get these kind of warnings. And another way in this case is to essentially solve it, and that can be done in this case by having this dot values that we have over here. Then we're going to have the predicted value stored in this predicted y that we have over here, and we can calculate then the mean squared error by comparing the say y values that we have with respect to our test sample, so the real values that we have with respect to the test sample, the real say asking prices, and we can compare that to the predicted asking prices that we have just calculated in the previous line that we have over here. And then well, we get the mean squared error. We're going to store that into MSE. Apart from looking at the MSE, it's in many cases also interesting to look at the R squared among the test sample, and we have already seen that before. We can do that by taking first of all the difference between, well, the values, the y values of the test sample and its mean, and then well, taking the sum of squared sum of squareds with respect to this diff that we have over here, and that will give us the total sum of squared residuals. And well, then at the moment that we are going to then well, we can print out the MSE then, but we can then also by this line that we've over here print out the R squared that we have among say the test sample. Well, remember that another thing we still need to do at the moment that we're going to do trees is that we actually have to do cross-validation. Take into account that based on the previous slide, we have here set the max depth equal to 10, but it's very unlikely to be the case that this is a very good choice. So therefore what we need to do is to do cross-validation in order to set this hyperparameter the max depth that we have over here. Question arises how we're going to do that. Well, for that it's good to look at the total listing with respect to the program that we have. Well, there we actually have a couple of different things. First of all, we have here our imports. Take into account that we do, of course, import here the decision tree regressor. But apart from that, we also have here mean squared error that we have already seen at the previous slide. We are going to have this train test split in order to get a training and a test sample in our analysis, and we have here k-fold. Then we have a couple of different constants here. We are going to investigate with respect to cross-validation between 1 and 40 with respect to the potential, say, optimal depths that we are going to have, and we are going to use 10 different folds, and our test size is going to be 20% of the total, say, sample that we have. Well, then the most important part is actually over here, but well, first of all, we get this function do cross-validation as we have it over here, but take into account that that one is exactly identical to what we had in the previous tutorial at the moment that we were looking at less or enrich. So therefore, I'm not going to say too much about that here. More important is actually the next function, and that is cross-validation. Again, it has as inputs the number of folds that we're going to have, well, the X values with respect to the training data set, Y values with respect to the training data set. And here we are going to look at the min depth up till the max depth. These values we already have introduced over here as constants. And then, well, the rest of it is almost identical to what we have already seen before at the moment that we did less or enrich. But now we are not going to iterate with respect to the values of alpha, but now we're going to iterate with respect to the value of the depth. And that we're going to do simply by a for loop, because in this case what we can simply do is to go on from the lowest, say, value that we want to look at, in our case 1, up till 40. Well, if we would have done just max depth itself, then we would have stopped already before 40, so therefore we have max depth plus 1 that we've over here in order to have exactly up till 40. And then we are going to look at the main part. We are going to have here the decision tree regressor. We are going to set the max depth equal to the depth, this depth that we have over there, and we are going to use a random state equal to 0. Question arises, what is that? Well, that we in many cases use at the moment that we're going to do our analysis in order to make sure that at the moment that we're going to do the analysis twice, that we get exactly the same result. And take into account that a part of the decision tree regressor is going to be based on something which is random. Therefore, we're going to set this random state equal to 0 just to have the correct seed. And then, well, we have here the calculation of the cross-validation risk that we do with respect to this function that we have just over here. But as I already said, it's exactly the same as what we already have seen with respect to when we were using less or rich. And actually the rest of this is also exactly the same. So then in the end what we would like to have, even though I still call it here alpha, what we would like to have is the best value with respect to the depth, and that is going to be returned by this thing over here. Well, then we are going to get our main function. The most important thing is after, well, doing the important things with respect to the data, then the most important part here is to split the, say, total data set into a training and a test data set, this train and test that we have over here. And well, as I already said before, then we need an I value, an X value with respect to our training data set, so that we get to over here and that we get over there as well. And then, well, the rest of it is again quite like what we have already seen before. Whenever we did less or rich, we now are going to do cross-validation. We're going to have the optimal depth from the cross-validation. In order to make sure that it's going to be an integer, I will put here this int over here. Otherwise, I might get an error later on if I try to input it here into the decision tree regressor. And then we're going to use then, well, the algorithm for the optimal depth as we have over here. And we're going to fit it, we're going to predict, and we are going to finally calculate the mean squared error as well as the r squared as we have it over here. And well, if we are going to do all of this, and well, this runs then perfectly. We still have to have these lines, of course, in the end. But if this all runs perfectly, then what we're going to see is that the test risk is going to be equal to 0.0463. So that's the MSE that we have just calculated. And then the corresponding r squared for the test sample is going to be equal to 0.8396. So far we see that this actually, well, is comparable to what we have seen already with respect to linear regression, but the, say, performance that we have with respect to these trees is by far not as good as what we have already seen with respect to lasso and rich regression.